Welcome. We are going to talk about the fundamental theorem of calculus for line integrals. We have a long way to go, so let's get started. Now, we know the fundamental theorem of calculus in two dimensions, and it basically says that if we want to get the area under a curve, we can find an antiderivative and we can just plug in the beginning and end points and subtract. So the question is, can we do something like that with line integrals? And so this is not actually a totally different theorem. It is just a new version of the existing fundamental theorem of calculus. But if we were to take one of our paths, say we want to a line integral, maybe goes along like this, let's say. And so up above there'd be this curtain shape, and we want to say, can we find the area of that curtain? Is there a way we could just plug in the beginning point and the end point and subtract and get the answer, same as we would in one-dimensional? Now, the complication in two dimensions, similar to with partial derivatives, is that there are a lot of different paths you could take. So, in one dimension, you just go left to right. There's really only one way to do that. But here, we've got lots of different courses we could go through. What if we did a spiral and went around it like 8 times, or however many? Does it matter? Well, that's the driving question for today's lecture is, does it matter what path we take? And if not, can we then just plug in the start and end point into something to get the answer? All right, so first I think we ought to define what a path is. There are going to be, I'll warn you right now, a lot of definitions in this particular video. A path is a piecewise smooth curve. That's really the definition, but let's spell that out a little more. It's a figure that can be parameterized by r of t is r1 of t, where t goes from a to some t1, r2 of t, where t goes from t1 to some t2, and so on down to rn of t, where t goes from tn minus 1 to b. So that's saying if we have a point A and a point B, we can have a first path R1, then another path R2, and another path R3, and so on until eventually we end up at the nth path Rn, which closes us off. Now the smooth part means that each of the Ri have non-zero derivatives. Except at endpoints. So along each of these individual paths, the derivative is not zero. Now, since there's a sharp corner here where we switch from one parameterization to the next, from one piece to the next, it may have to be the derivative of 0 there, but we don't really worry about that because there's only finite number of them, and so therefore we could just do them one at a time and add them together when we're doing our integral. So we're going to say, we're going to give a pretty, I hope, obvious or intuitive definition here. So definition. So given a continuous vector field, VF stands for vector fields, because I have to write that a lot, capital F, with domain D, we say the integral f dot dr along C is independent of path. Provided the integral along C1 f dot dr, oh, this should have a vector arrow on it, is equal to the integral, sorry, I'm thinking of complex. Now they have those little circles on them. Don't worry about what that means. That's something else. Maybe it'll come back later. FDR. I guess the R's are technically vectors as well. For any C1 and C2 that are contained in D with the same endpoints. So what does that mean? Well, a domain, and we'll just assume that this F is in, the domain is in R2, but it could be in R3. So I'll draw a big set like this. I'll call that D. And I'll say we're doing some integral from A to B. And so let's say this is our curve C. Well, if this is independent of path, that means we could take any other path from A to B and get the same answer. Okay, so how do we know if we can do it? When can we do this? When are we going to be path independent? Well, before we defined a conservative vector field as something that has a potential function. So here is the theorem that line integrals of conservative vector fields are path independent. So just as a refresher, that means that we have some domain D, and on it we have f is equal to the gradient of some little f. If it's possible to write f as the gradient of some little f, then that's going to be the case. So we can show that using the chain rule. I don't think I did that. I don't think I showed it yet. Maybe I'll put in the proof as like a supplemental. So that is the test. If we can show that big F is the gradient of some little f, where f is a scalar function, so f of x, y equals z, whereas capital F of x, y will be like, pi plus qj, maybe plus rk, maybe. Could have any number of components. But if we can break it down, we can say it is the, I guess if there's only two variables, it should only have two. But yeah, okay, so if we can break it down like this, then we know that it is, the path doesn't matter. We'll try to give an idea of why that is as we go. So, I guess, yeah. All right, so let's do another definition. We'll get to some examples soon enough, I promise. But, okay, a curve defined by some RT, where t goes from A to B, is closed provided R of A equals R of B. So that just means that when you plug in the start point, it travels around for a bit, and when you get to the end point, it's back where it started. And there were little arrows here to indicate the direction. Direction matters a lot in this, by the way. We're going from A to B, and if A and B are the same thing, then it matters whether we're going clockwise or counterclockwise. All right, so now let's do one more theorem. This one I think will be not too hard to justify just by picture. We'll say theorem, integral, I did that again, didn't I? Integral along C of f dot dr is path independent in D if and only if, I double F means if and only if, integral of f dot dr along C equals 0 for all closed paths C in D. So I'm just, like I said, I'm just going to do a proof by picture here. I'm not really going to try to give a fully rigorous thing. But the idea is we have a domain D, and we say here is a path C1, and here is a path C2. Are these equal? Well, if we were to do the full circle, let's say C was the entire thing. Sorry, let me try that. That doesn't make sense yet. Say I wanted to do C as C1 minus C2, meaning I would first go this way along C1, and then I would continue this way along C2, but backwards. Well, the integral of f dot dr we've just told, we're saying if it's 0, then that means the C1 integral minus the C2 integral is also 0. But that's the same as saying they're equal to each other. So, like I said, the picture explains it pretty well. What we're saying is that if we did a full loop, we get 0. So we first get a certain amount, get a certain value from C1, then we do C2 backwards, we have to erase all that, so it must be the exact opposite. So therefore, if they were in the same direction, they would give the same thing. Now this really gets into the whole idea of conservation of energy, because what we are saying, conservation of energy, if I follow a path, come back to where I started, I have not lost anything. So we're on a frictionless slide. Maybe it's a roller coaster. A roller coaster is not perfectly conserving energy. It loses some to friction. But if there were no friction, then you could start at the top, push down, your roller coaster would gain energy, it would get as fast at the bottom, then would slow as it went back up. And as it got to the very top, it would come to a perfect stop, because no energy would be lost at all. So it's the same idea then. The energy to go from point A back to point A will always be 0. So therefore, the energy to go from point A to point B in this direction would be the same as if you went in this direction. And so it doesn't matter how many loops and curlicues you make, nothing really happens. All right. So I'm going to want to talk about open sets. What's an open set? Well, and what's a connected set? Now this is the sort of thing that can get tricky. We're not going to make it too hard. If you ever take a class in topology, it gets a good bit more complicated, but we're going to try to make it as intuitive as possible. A set D is open provided every point in D is the center of a disk in D. So graphically what this means is that there's no boundary. The boundary is missing. If I pick any point inside, I could draw a little disk around it that would be entirely inside. Now if the boundary were included, we wouldn't be able to do that, because if you picked a point at the boundary, disk would have to fall outside of it. So if that's too much, just think of it as it's a set that the boundary is missing. Okay? A set is connected provided any 2 points in D, the connected set, are endpoints of a path in D. Okay. So we're going to want our sets to be both open and connected in most cases. The open is mainly because derivatives don't really work very well at boundaries, so we want to take the boundary out. And the connected is so that we have paths that we can draw between any 2 points, and so we don't have to worry about falling out. What do I mean by fallout? Well, let's say here's an example of a set that is not connected. It's this and also this. So like everything inside this bubble combined everything inside this bubble. This is not connected because if I picked a point in the first bubble and a point in the second bubble and tried to draw a path between them, I would have to leave. I would have to go outside the combined set D. So this is not connected. Here, this is a set that's not open because it includes part of the boundary. Here's a set that is both open and connected. Any 2 points, I can't draw a straight line between them, but I can draw a path that connects them. Okay, so open connected sets are one. This is both open and connected. And we're not going to try to give you too many tricky ones. Like, I don't plan to give you a bunch of weird sets and you'll have to think, oh, does this count or not? Let me think back to my definitions. Most of the problems we're going to do in this class will just stick with open and connected sets, possibly closed ones on occasion. But here's the thing. If this were a really advanced analysis class, they might give you a bunch of weird domains and you'd have to guess, or well, you'd have to deduce whether or not you can use the theorems. We're basically going to keep to situations where you can use the theorems in this class whenever possible. So, suppose F is a vector field that is continuous, CTS stands for continuous, on an open, connected, con apostrophe D stands for connected, set D. So, if F dot dr is path connected, no, sorry, is path independent, excuse me, is path independent on D, then F is conservative on D. So let's see. We already said the opposite. We said if the vector field is conservative, then the integral is path independent. So now we're doing the opposite. If it's path independent, then the field is conservative. Yeah, like I said, I'm going to skip over the proofs for now. I think I'm going to put those in a separate video. All right. So, we'd really like a simple test. If we could tell it is conservative, then we know if it's path independent right away. So, this is, I always try to, every lecture, try to get one big theorem or emphasize what's the biggest one. And this is going to be the big one here. So here is the test for conservative vector fields. Maybe this is not the big one, but it's definitely one of the big ones. All right, so we're going to write F is Pi plus Qj. And suppose F is conservative and smooth. And smooth just means that you can take the derivative as many times as you want. I mean, we said we said what a smooth path is. For a vector field, it just means you can take the derivative as many times as you want. And so, the derivatives are all continuous. So, our theorem just says, because it's conservative, we know there exists a little f where gradient of f equals big F. That means del f over del x is p, and del f over del y is q. So since we said big F is smooth, we can, well, let's take the other derivatives here. So, so I'm going to say, let's do del over del y to this one. So this would become del squared f over del y del x. And then let's do the x derivative here. So del squared f over del x del y. Well, if you remember when we first did partial derivatives, we said Clairaut's theorem says that as long as the function is smooth, which we said this is, then these things are equal. So that means del p over del y equals del q over del x. So that's the test. This is the thing that you'll want to copy down and memorize. This is how you test whether it's conservative or not. Usually. Or rather, what we've just said is if the function, if the vector field is conservative, then this is true. Can we do it the other way? Can we say, if this is true, then the function is conservative? And the answer is usually. So the theorem we just said is that if f is pi plus qj, and p and q both have continuous first partial derivatives, on D, then this is true. Del P over del Y equals del Q over del X. Anyway, let's see when can we use the test? Well, there is a couple more conditions. And so definition, let's be quick about this. A simple curve is a curve that does not cross itself. Does not intersect itself except maybe at endpoints. So this curve is simple but not closed. This curve is closed but not simple. This curve here is both closed and simple. And then there is one more definition, and this is probably the most complicated one, so I'm going to try to simplify it. A simply connected region is connected and has no holes. So something like this, that is not simply connected because there's a hole in the middle of it that's just undefined. If we had something like this, that is simply connected. Let's pretend that closed properly. There's no holes in it. There's this weird, divot, but it's not enclosed. There's nothing like trapped inside it. Something on the inside could get out. Something like this, Pac-Man here, not simple. That is simply connected because again, there's no holes in it. All right. So we want to stick with simply connected regions with possible. We want to have regions with no holes in them. And that's because this. On an open, simply connected domain, if P and Q have continuous first partials, and del P del Y equals del Q del X, then F is conservative. Okay, so this is kind of the main thing we've been going for. We found this thing here. We can use it and do some examples. And so I'll do a few examples. There are more in the book that you can work on. But let's do one right now. So let's take the function f of x, y equals x minus y I plus x minus 2 j. Ugly looking j. All right. So what is the domain of this function? Well, domain is all of r squared. There's no combination of x and y where this thing would be undefined. So that means it is simply connected because r squared itself goes out to infinity in all directions, so it doesn't have any holes in it. So let's do the test. The first one is P, the second one is Q. So del P over del Y is -1. And del Q over del X is +1. Those are not equal. So this is not conservative. Okay. What about, take a new function. F of xy equals 3 plus 2xy I plus x squared minus 3y squared j on r squared. Well, I don't necessarily need to tell you that, but generally speaking, domain, we should always use the largest domain possible unless we're told otherwise. So there's no obvious reason why we should restrict the domain. There's no, denominators that could be 0 or anything like that. So we'll just let the domain be everything. So is this one conservative? Well, del P over del Y is 2x. Del Q over del X is also 2x. Yes, it is conservative. So it is worth, this is called the curl, and I try to give kind of a visual idea of here. I'm not sure I can do this super well, but you'll notice how they're sort of crossed. Like P is the function that determines the X output versus the Y input. And Q, that's the Y output versus the X input. And so it's sort of like they sort of cause things to curl around. Because it's sort of like it's a twist. It's how the Y goes in versus the X that comes out, and the X that goes in versus the Y that comes out. And so what we can say, another way of saying this would be that del P del Y minus del Q over del X is 0 everywhere. We'll talk more about it, I think, after break. But this curl here sort of represents how much rotation is going on. So if you're saying, is it path independent? Well, the path you take, if there's a lot of little, winds going in circles around here, then you could end up wasting a lot of energy trying to overcome that. But if you don't have to deal with any of that, then all that matters is getting from point A to point B, and there's nothing there to waste the energy. I guess you could also think of it kind of like friction. It's just what goes to waste based on your path. So another way to remember this, then, you can make a little vector or a little matrix here. You can say PQ, make sure I'm doing this right, del over del X, del over del Y. And so, so that, if you did this matrix here, del P del Q minus del Q del X. Or del P del Y minus del Q del X, sorry. So I like this way, and when we get into 3 dimensions, we'll have to do something similar. I'll say, for one thing is, and another, in the next unit we do, we'll have to use this quantity a lot more, and I always forget the sign, so writing it this way helps me remember what the sign is. So That's just another way of writing it, really, though. It's that you can say this thing is equal to 0. That's another way of being conservative. I feel like this section needs to be streamlined, but they do give a lot of definitions in the book, and I wanted to go over them. Let's sum of this. All right, a function like, let's do an example here. F of x, y is, let's say it's 1 over x squared plus y squared, I plus j. Well, the domain has a big hole right in the center. So this is not simply connected. So if, for instance, we were trying to integrate f along some path, well, it's not conservative. Or what was our rule? We can use the test to find out if it's conservative. Our little test we do here, the del p del x or del q del y, would not work here. So we'd have to find some other method. Probably we'd have to parameterize this and work it out directly. Because So since it's not conservative, for instance, if this is c, integral of f dot dr, we said before, on a conservative, every closed path, the integral should come out to 0. This one is probably not 0. It is interesting to me how just having this one little hole in the middle throws off everything. Like, if only there were if only this didn't have this hole in here, then this integral would automatically be 0. Well, we'd have to check the conservative property first, but if it met the conservative property and there was no hole, it would be 0. But there is, and so that changes it. It's probably like 2 pi times something, because the number of radians around is 2 pi. And so this is getting a little far afield, but if you take complex analysis, which to my mind is the best course to take right after multivariable calculus, that comes up all the time. This sort of integral is a very common problem. Like, what is the integral of a closed path when there's a hole in the middle? All right. So we're now going to move on to the more computational side. And so if all the theory we've done so far has confused you, I understand. The theory stuff is a little hard to grasp when you're first learning it. So we're going to now work out some computations. And quiz on Monday will probably be something similar to one of the problems I'm going to show you in this section. So, if f xy is 3 plus 2xy I plus x squared minus 3y squared j, find the potential of f if it exists. All right, so we are going to look at this. How do we do this? Okay, first off, let's check if it even has a potential. So that means we need to check the del p over del y equals del q over del x. That was one of the earlier, we already did this problem. This was one of the earlier examples, and we saw that was actually the case. So we can go ahead and check that off. but you can do it again if you need to verify for yourself. The y derivative here would just be 2x. The x derivative here would also be 2x. So, how are we going to track down the potential? Well, so this says f exists, and the gradient of little f is big F. So let's split this up into pieces. This is saying that, for instance, del f over del x is equal to p. And this is p, this is q. So that means 3 plus 2xy. So we can do an integral to work out what f is from this. So this is the same as saying df, or del f, is 3 plus 2xy dx. Now we integrate both sides, and again, I'm not all that picky about whether you use the partial d or the regular d. I don't care that much. Some people get really picky about it. I don't think it makes that much difference. So f is equal to, so the integral here, 3x plus x squared y plus constant. But here's the thing about this. All we know is that the derivative of this, the x derivative of this, is 0. That doesn't necessarily mean it's a true constant. It just means it has no x in it. It could be a function of y. So keep this in mind. We did the x integral, so the constant term that comes up must have no x in it, but it can have y's. All right, so we're partway there. Now, we know that from before, what was f? Del x, or del f del y, sorry, is x squared minus 3y squared. But we could also do the y derivative here directly. Del f over del y is 3 plus x squared plus c prime of y. And so we can set these equal to each other. Or, hang on a second, I make sure I think I have a mistake in this somewhere. Okay. Oh yeah, it's fine. So these two things are equal to each other. So we have x squared minus 3y squared equals x squared plus 3 hold on, I feel like I need to check my notes. I feel like I want to make sure I'm not making a mistake on this one. X squared plus the y derivative is, oh, you've probably all been yelling at me for the last couple minutes. The y derivative, that 3 should not be there. I did the x derivative by mistake. Okay, that clears it up. So, x squared plus c prime of y is equal to x squared minus 3y squared. So those go away. Sorry. Let's do this right. X squared minus 3y squared equals x squared plus c prime of y. Those are gone. So, negative 3y squared equals del c over del y. So we'll do the integral. We'll put the dy there, the dy there, or the integral there. So c equals negative y to the third plus constant d. All right, so now we can take that and plug it back in here. So minus y cubed. Plus d. Now, the plus d thing is kind of unnecessary, and the reason is because we want to find a function whose gradient is capital F. Well, when we do derivatives, no matter which derivative it is, the d is just going to vanish. So it can really be anything, so we might as well just make it 0 and just ignore it. So that means the potential function is actually not unique. It can shift by a constant. Let's test this then. What is gradient of f here? Well, the x derivative, we do 3 plus 2xy, and the y derivative would be x squared minus 3y squared. Is that what we started with? Yes, it is. So we're done. We found it. That's our potential function. Now, with that said, we can now actually state what the fundamental theorem of calculus for line integrals is. And I am going to, for some reason I don't have it written in my notes, so I'm going to open up the textbook just to make sure that I don't leave anything out. But, as we said, for regular one variable integrals, the idea is that we can take an antiderivative and we can just plug in the endpoints. Well, let's do something similar here with the potential. Okay. So here is the definition then. Here's the theorem. All right. Let C be a smooth curve given by R of t, where t ranges between A and B. And let f be a differentiable function, so a function we can take derivatives of 2 or 3 variables with gradient capital F. Then the integral along C of f dot dr is the same as little f of r of b minus little f of r of a. So what's it saying? This is the end point. This is the start point. So just like how in one variable calculus we plug in the beginning and end points and subtract, we do the same thing here in multivariable calculus. We're plugging the beginning and end points and subtract. We're plugging them into the little f potential function. So our main goal is just going to be to find the thing, and then we can just plug in. So let's do an example of that. All right. Evaluate the integral along C of f dot dr, where f of xy is that same function, 3 plus 2xy I plus x squared minus 3y squared j, and C is the curve given by r of t is e to the t sine t I plus e to the t cosine of t j. Where t goes from 0 to pi. So the curve here would go, if we start at 0, we'd get I component would be 0, j component would be 1, so it'd start up here. And then as we increase, they will both get larger magnitude. Cosine is I, sine is j, so I think it's going to be something like this. I mean, what would the endpoint be? R of 0 is e to the 0 sine 0 I plus e to the 0 cosine 0 j, which is just 1j, I suppose. So it's 0, 1. And if I plug in the endpoint, r of pi would give you e to the pi sine pi I plus e to the pi cosine pi j. Now, sine of pi is 0, so that's gone. Cosine of pi is negative 1, so this ends up as negative e to the pi j. So down here somewhere, 0 comma e to the pi, negative e to the pi. You can look up the decimal if you want. It's pretty big. I think it's like 10 or something. Oh, it's like negative 23, my notes say. So anyway, if you look at this function, what we would have to do, we'd have to take this and plug it in for these x's. This, plug it in for these y's. Then we would have to take that, dot it against this, no, against r prime. We take the derivative of r prime, so there's some product rule in there. Then we have to do dot product. Then we'd have to do the integral from 0 to pi. And that sounds very unpleasant. So instead, we're just going to say this vector field is conservative, and we know its potential function. So we can just plug in the beginning and plug in the end. So I'll say the integral f dot dr along C, or this is C, and again the direction does matter, would be equal to f of the endpoint, 0, negative e to the pi, minus f of the start point, 0, 1. And now our potential function that we just found was 3x plus x squared y minus y cubed. So this would equal, let's see, plug in 0 for x and 1 for y, so we'll get negative 1 minus, and plug in the first part, plug in 0 for, I did it backwards, didn't I? Sorry. Let's see, we plug in, okay, so let's try that again. Plug in 0 for x, so those first two terms disappear. We get negative e to the pi to the third minus, plug in 0, 1, so that zeroes out, that zeroes out, we get a 1 here, so negative 1, or, is that right? Plug in 1 here, negative 1. And so this becomes e to the 3 pi plus 1. Did I do that right? It's... No, sorry, there's no negative there. What am I doing? I'm sorry, everyone. This is, I'm making some mistakes here, but hopefully this is not too confusing. We end up at the right place. Okay. So you see what I'm saying. The point here is that once we found the potential, we don't need to bother with parameterizing paths. We can just do beginning minus end. And it's similar to the roller coaster idea. In fact, there's a reason why you talk about potential energy. I remember this is something I learned back in first physics class, back in high school, I think. It's like if you have there's a potential energy formula. U is mgh. I think they use U for that. And the idea being that you got some complicated path. You could work out all the details of the path, and it would be a lot of work. Or you could just say, here is H max, and here is H min. And you could just say the change in potential energy would just be mg times H max minus mg H min. And so all you had to do was get the energy at the top minus the energy at the bottom, and that's how much energy has been lost, and that's why they call it potential energy. This goes back to Mr. George Green, who came up with the idea of the potential function, meaning a scalar function that carries all the information about this complicated vector, because its gradient is the vector. So I use these a lot in my own research. I'm writing up in my dissertation right now. The idea being like you've got some sort of charged plate. You all know we got some particle out here. Well, the electric field that it creates is conservative. So if you want to say how much work is done to move from here to here, well, you can work out a potential function, and instead of the complicated integrals that's involved in doing it directly, you can just work on the potential and plug in the start and end point, and that'll tell you how much work it takes to move from point A to point B. There is an alternate method for doing this problem. Let's look at that last example again. I would say f of xy is, what was it, 3 plus 2xy I plus x squared minus 3y squared j. And we want to go from the point, it was 0, 1, down to 0, what was it, negative e to the pi. And they told you take this weird path like this that was really hard to parameterize. So you could do this. You could say, I do the start. I check to see if this is conservative. And I check that it is. It is. So you can say, since C or F is conservative, it is path independent. So we saw find the little f might take a while. So instead of that, you can just say, I know it exists, so that means I can just take any path I want. So what if I just want to go straight down? Nothing's stopping me. So the parameterization R of t is x is always 0, and y, I guess, would be, let's say, negative t, where t goes from negative 1 to e to the j. T always has to increase, so we just use negative t. So at the beginning, you plug in negative 1, you get 1. Plug in e to the pi, you get negative e to the pi. And so you could do this. You would say integral of f dot dr is, let's see, r prime would just be 0, negative 1. So this f dr would just be 3 plus 2xy comma x squared minus 3y squared dot 0, negative 1 dt. So we can replace all this x's with 0, so that goes away, that goes away. And so this will give us integral, where t goes from negative 1 to e to the pi of 3, negative 3, negative t squared dot 0, negative 1 dt is negative 1 to e to the pi of 3t squared dt, which just becomes negative 1 to e to the pi of t cubed, which is e to the 3 pi minus 1. So same result. So pros and cons here. Pro, this way, once you know it's conservative, you can just make up a new path that's easier, and you don't have to spend time finding a potential function. Con, you still have to come up with a path, and it may not be there's one that cancels out quite as nice as this. Whereas if you have the potential, you don't need to worry about paths at all. You just plug in the start and end points and subtract. So, depending on the problem, one way might be easier than the other. All right, so I'm going to do one more big example, and then I'm going to call it. I'm going to do a 3-variable one. So let's say we have f of x, y, z is y squared I plus 2xy plus e to the 3z j plus 3y e to the 3z k. And so I'm going to say, find a potential. Now, how do we know this exists? How do we know it's conservative? Well, we will give a test for that in the future. For now, I'm just going to go ahead and tell you this is conservative, and so there is a potential function. We just have to find it. So, there's some f where del of little f equals capital F. So we're going to go through this one by one. All right, so del f over del x is y squared. So we can solve this as df is y squared dx. Then we take the integral of both sides. We get f equals xy squared. But we now need the constant. And in this case, since we only integrate in terms of x, the constant could have both y and z. So we get c of y z. Okay, so I recommend at this point put like a little star here next to little f, because as we go, we'll find more and more parts of it, and we'll want to just be able to go back and plug in. All right, so let's look at the next component. We have, all right, so second part is the y derivative. So it is del f over del y is 2xy plus e to the 3z. So now we'll take the f that we found from the earlier part and do its y derivative. Del f over del y is 2xy plus del c over del y. So we'd set these equal. 2xy plus del c over del y. So then those are gone. E to the 3z equals del c over del y. So let's see. So let's do the antiderivative there. C would equal e to the 3z, or dc is e to the 3c dy. Let's take the integral on both sides. We will get c equals y e to the 3z plus, now we did the y derivative, or the y antiderivative. We've already established c does not have any x's in it by the way we built it. And now we know when we do the y derivative, this constant will not have any y's in it. So we'll be left with a d of z. Okay, so yeah, so see, we're knocking out one variable each time. So instead of c, we can now replace that c with this thing that we just found. So we're getting closer. We still need to figure out what d is, but we're almost there. All right, so we now just need to do the z derivatives. So let's look at what we should get. We should get this, 3y plus e to the 3z. So del f over del z is 3y e to the 3z. Now let's do the z derivative here. Del f over del z is 0 plus, okay, y is a constant. The z derivative of e to the 3z would be 3e to the 3z. So 3ye to the 3z plus d prime of z. Okay. So these are equal. So this is equal to 3ye to the 3z. Well, that means we can cross those out. So we're left with d prime of z is 0, which means that if the derivative of d is 0, then d of z is a constant. It's a true constant, in fact. It doesn't have any z's in it. So it's just z. But we said that that doesn't actually matter. Constants are capable of being ignored. We'll just take out d. And that then is our actual potential function. And whenever you're doing this, I encourage you to check. Gradient of f equals y squared 2xy plus e to the 3z and 3ye to the 3z. You can check that on your own if you like. So that's the answer. And like I said, it's not unique because, again, going back to the roller coaster example, if we go from here down to here, a certain amount of energy is spent. If, on the other hand, the roller coaster were just built in a different place lower down, but the exact same path, it would be the same change in energy. The idea is that the potential function tells you the relative change between 2 points. So where they start doesn't matter. If this is the path and we shift it to some other place, it won't matter because it's still the same relative change between the two. So that was a lot, and a lot of it is theory. Like I said, we're going to try not to get into any weird pathological examples. We're going to mostly stick with ones that are simple and connected and that you can find a potential function for, or that an easy test shows that you can't. So yeah, that's pretty much everything. Email me if you have any questions. Otherwise, I will see you in class.